So we're going to be talking about finite basis sets in quantum chemistry. So first question is really, what is quantum chemistry? And it comes down to solving the Schrodinger equation, which hopefully people will have heard of, even if they're not familiar with it. It's a diffusion type equation, first order in time, second order in position normally. But we're going to narrow this problem down. So quantum chemistry is fundamentally concerned with solving the Schrodinger equation for molecular systems. We're interested in electrons and nuclei. And just for an example of scale, if we wanted to look at even a milliliter of water, that's on the order of 10 to the 9 degrees of freedom. If we wanted to look at any kind of realistic system, it becomes impossible. If we want to look at a protein, for example, it's essentially impossible, although that is somewhere where work is going. But we're going to narrow this down to what's called the molecular Hamiltonian version of this equation. So the molecular Schrodinger equation, which is, you can see here, the molecular Hamiltonian is not dependent on time. It just has a kinetic energy term, is the first term in the middle, and a Coulombic term between, so you've got an attraction between nuclei and electrons, and a repulsion between nuclei, repulsion between electrons. That allows us to separate the equation out into the time-independent Schrodinger equation, which is just an eigenvalue equation, H psi equals E psi, which is one of the most famous equations in science. Typically, we go even further than this in quantum chemistry, and we separate out the nuclear and electronic coordinates. This is called the Born-Oppenheimer approximation. We don't have to make this approximation, but for simplicity in this talk, I'm going to assume that we only really care about the electrons, that the nuclei are fixed. And what that means is the only complicated term left in our Hamiltonian is the electron-electron repulsion. And that pesky Coulomb repulsion term causes all sorts of difficulties. So moving on. The simplest possible molecular Schrodinger equation we could look at is for the hydrogen atom. So that's actually one nucleus, one proton. The nucleus is one proton and one electron. And of course, if we're fixing the proton, then that means that we essentially have just a one particle system, and we can solve that exactly. And the solution is given here. It looks more complicated than it is. Essentially, the bit that we care about is you've got spherical harmonics that always appear. You've got a generalized Laguerre polynomial at the beginning, which is what gives it its funky shape depending on angular momentum. But the really interesting part is the Slater, what's called the Slater function at the end, which is just a simple exponential in the radial distance. And then if you solve this for the free quantum numbers, so this is where the whole idea of quantum mechanics came from, is that when you look for solutions to the Schrodinger equation that satisfy the boundary conditions, the energy for the bound states become quantized, and those levels are determined by free quantum numbers in molecular and atomic systems, and those are the principal quantum number n, the angular momentum L, and the azimuthal number m. We're not really interested in the azimuthal number, but n and L are very important. So n essentially determines the energy, and that's the first number in these orbitals that you can see these pretty pictures of here. I don't know why some of them are rainbow colored and some aren't. This was just a copyright-free image that gave a good representation. And then the angular momentum effectively determines the shape. So angular momentum 0 will typically have, will always have spherical symmetry, and then we call those the S-type orbitals, and then you get the P and the D-type orbitals, and they have these distinctive shapes. And if you talk to any kind of experimental chemist, they think in terms of these orbitals all the time. And I often have to explain to them that they are just mathematical artifacts and they don't actually exist, but that's a debate for another time. If we move on from this, however, if we want to look at anything bigger than a hydrogen atom, we need to try and find a way of solving the many body problem in a way that we can actually do on a computer. And that's basically, if the overarching sort of area that I work in is trying to make this problem tractable without losing accuracy on modern computing systems in a reasonable amount of time. What that actually mostly comes down to is in a reasonable amount of memory. But again, that could be another talk. So we have an extra requirement on our solutions that you don't have in a lot of quantum systems, which is that we are interested in electrons, so they're fermions, and fermions have to obey Fermi statistics. What that basically means is that if we permute any two electron coordinates, so space and spin coordinates, these bold are, then the sign of the wave function has to change. What this effectively means is that you might think that a simple way of solving this is to just write a product of one electron functions, which is called a Hartree product, after one of the early sort of quantum chemical theorists. But the problem with that is that that obviously doesn't obey Fermi statistics. So the simple solution due to Slater was just to write them as a determinant, where we anti-symmetrize according to the totally symmetric group these Hartree products. We can then expand the total wave function for a molecular system in terms of every possible Slater determinant with n electrons. This is assuming that we have an infinite one particle basis, and you can show quite easily that the eigenfunctions of the hydrogenic Schrodinger equation do form a complete one particle basis in an n electron Hilbert space. What we then end up with, however, is because in chemistry we're not just interested in problems where the number of electrons are fixed, we don't have conservation of the number of electrons. We are also interested in problems where we go between so for example, electron attachment or electron ionization, where you're losing or gaining an electron. So what we end up with is this set of n electron Hilbert spaces. They're L2 type spaces, if that's something you're interested in, because the wave function has to be square integrable. And the direct sum of all of those n electron spaces is called Fock space, and that is where all of that theory happens. We then want to solve this on the computer, and this is all pretty sort of standard in terms of sort of mathematical discretization of PDEs. This is all stuff that hopefully people will be at least vaguely familiar with. There are some interesting theoretical properties from my point of view as an analyst, in that you can show that with that infinite one particle basis, that if you do have every possible n electron determinant with which is finite, not finite, is countable. It is an exponentially explosive set of determinants, but it is countable. Then that can be used to form the exact solution, which isn't as obvious as it sounds, because we're going from a hydrogen atom where there is no electron correlation to a problem where there is electron correlation. Electron correlation is that electron-electron interaction, the Coulombic term I mentioned before, that causes all our problems. So basically, what this means for me is that I can reduce the problem down to just the one particle basis set. Even if you truncate the one particle basis to a finite basis, which obviously we have to do on a computer, if we include every possible what's called configuration, which is basically every possible electron determinant, then we still have the exact solution within that reduced problem. So that's nice. The problem then is about how do we choose a finite one particle basis, and that is the main aim of my work that I do at the moment, and it's quite a bit of research that I've looked at before. And this talk is largely about a theoretical property of basis sets that everyone has ended up using almost universally in quantum chemistry. And specifically, the question is, does the finite basis set that we have chosen to use, is it possible to form a complete basis set in the limit that we had infinitely many of those functions? So can we consistently converge towards the exact solution with these basis sets? And that is quite a difficult question to answer, and it's one that's gone more or less completely unanswered in this area until quite recently. The spoiler alert is that the answer for mean field methods, so what I've written on here is that this kind of comes into two problems, and we're going to focus on one of them. One of the problems is that if you only have a single slated determinant, so that's these anti-symmetrized products of one particle functions, then if you looked at a two electron wave function built in this way, and you looked at the probability which is related to the wave function squared, that it essentially decomposes into the product of the one electron functions, which means in probabilistic terms that it's uncorrelated, which means that we're not treating the electron correlation properly. There is a significant amount of physics missing. And that's because we do need to include these other determinants. However, that still is a good zeroth order solution, and it is what's typically done. We are essentially replacing the electronic Hamiltonian, so the molecular Hamiltonian with the nuclei fixed, with a one body effective potential, which is called the Fock potential. Again, coming back to Fock space and the idea of that, which is normally written in terms of what are called excitations and de-excitations. We don't need to worry about that. And chemists like to talk about that as being the motion. I hate this terminology, but it's a good sort of simplistic way of thinking about it, which is it's the motion of a single electron in the averaged field, the mean field of all the other electrons, which is why it makes a good zeroth order approach. This is just a standard Galerkin problem. It looks like a simple eigenproblem, but that's not true, because the Fock operator itself depends on the wave function because of this average potential. And that leads us to the second problem, which is that to solve this problem, we need to have these integral elements at the bottom where we integrate the slated determinants over the Fock operator, which itself depends on slated determinants, and you end up with something called self-consistent field. Well, there are two variants of this: Hartree-Fock self-consistent field and density functional theory, which some people may have heard of. And in both of those, we are essentially using this mean field operator. We're discretizing it, solving it in the standard way. And the question that we want to know is that with a particular choice of one particle basis for this problem, will we, in the limit that basis increases, will we converge towards the exact solution? I'm actually going to go a bit further than this, and the only assumption I need to make on the one body potential, the only assumption I need to make on it is that it's regular. Essentially, that it commutes with its Hermitian conjugate. But that encompasses DFT and Hartree-Fock, which are the two mean field methods that everybody in quantum chemistry uses. Okay, so just very quickly, we'll have a quick look at qualitatively what happens when you go from the simplest possible system, which is a hydrogen atom, to the next simplest system, which would be a hydrogen molecule. So in this one, we've got two nuclei, so two protons at a fixed separation, and two electrons, which in reality don't belong to anything, but chemists, and it makes a lot of sense, like to think as each electron belonging to each atom. And then a chemical bond is formed when we allow that electron density to relax, and we see something in the middle. So this picture here is, if you just took the two atomic solutions and didn't let there be any correlation between them, these are what the Slater functions look like, projected into one dimension. If we add in just the nuclear electronic potential, so that's an attractive one body term, because we're fixing the nuclei, then it will look like this. So you can see that in the middle now, so the black line is the new one, the blue lines are the atoms just by themselves, and we get this chemical bond where we've got this sort of increased probability of finding the electrons in the region between the two atoms. The difficult thing then is to try and exactly add in the electron-electron repulsion, because that's a two-body term, and a mathematician called Heileras in 1933, I think it was, managed to come up with an essentially exact solution to this. The problem is you might think that the thing to do here is to use perturbation theory, but we have another problem in quantum chemistry with the electronic Schrodinger equation, which is that basically with few exceptions, most perturbation solutions will diverge. It was Kato proved that basically if there are any singularities on the unit circle in the complex plane, then it will diverge and diverge quickly, and that's not very useful. However, through a very early version of renormalization, we can get the solution for the hydrogen molecule. And these are level curves. So this is representing the probability of finding an electron. This is probability of finding electron 1. So electron 1 nominally attached to the atom on the right. And then as the black lines go down, that is electron 2 nominally attached to the atom on the left, moving closer towards the right. So as the lines go down, the second electron is moving from left to right. And you can see how they are changing the shape of the wave function. So they no longer actually look like Slater functions anymore, except at the nuclei where they have these cusps. And that's interesting because if you write down the first order term for the exact bit in the middle, it's called a Gaussian geminal. And that's interesting because the function that everybody uses, the basis function that everybody uses in quantum chemistry, is the Gaussian function. So instead of a simple exponential of the form there is phi s, the Slater type function, r to the L e to the minus r over n, we instead have a Gaussian function. So dependence on r squared rather than r. The upshot of this is that Slater functions decay slower and have a cusp at the origin, so discontinuity at the origin, whereas Gaussian functions have no such cusp at the origin and decay much more quickly. However, the integrals, the ones I mentioned earlier, integrating over the Fock operator with Gaussian functions is exceptionally easy, due to the fact that the product of two Gaussians is itself a Gaussian. Whereas doing that kind of integral over Slater type functions is very, very computationally difficult. So what happened in the 60s when they were trying to do this on very small computers was they decided, well, we're going to try and approximate Slater type functions by Gaussians and do all of our calculations that way. This was based on the unwarranted assumption that Slater type functions were the best possible one particle basis just because they matched some of the hydrogenic solutions. Fortunately, someone did then prove that there is a necessary but not sufficient condition under which Slater type functions do in fact give the best possible representation. But it was a bit of guesswork. But anyway, we use these Gaussian type functions, and then the assumption why this is an important question. The assumption is that as we increase the size of the basis set, so on this graph here on the left, n is called the cardinality of the basis set, and it basically just means the bigger n is, the more functions there are, the more exponents there are. And we assume that the Hartree-Fock or DFT energy is going to converge to the quote-unquote exact result as long as we keep increasing the size of the basis set. And the reason this is very important computationally is because people have taken this assumption and fitted curves to it, like you can see here, and said, well, we only need to calculate the first 2 points, and then we can just extrapolate. And that is a pretty heavy assumption to make. So getting to the main question, bear in mind I've got 1 minute left, so I've talked a bit slower, but I'm not going to show you any proofs. I'm sure you'll be happy to hear. Basically, previously, completeness for the Gaussian type basis was only shown for the supremum norm, so L infinity. And what this slide is basically saying, and I'll skip over it based on time, is that that is not the correct norm to use. It's not at all rigorous in answering this question. And the reason for that is that we have this differential operator in the Hamiltonian. So the convergence of the energy, the completeness of the wave function, the relevant space is either going to be H1 or H2, so the first or second Sobolev space. Fortunately for us, that operator is Hermitian, so we actually only care about H1, which makes things a bit easier. This is just to show how long this went unanswered. The last result related to this was by Klan and Bingle in 1977, where they showed a necessary but not sufficient condition for when Gaussian and Slater-type functions would be complete for the mean field solution. And in summary, it basically is that if there is, it's basically only a situation where this is a useful theorem to actually practically apply is if you have what's called an even tempered basis set, which is where there's a fixed ratio between exponents. But it was interesting nonetheless, and I used it. And then what I proved last year, well, 2 years ago, but published last year, is that for any system where you have a regular one-body potential operator, that both Gaussian and Slater-type functions, but most interestingly, Gaussian in this mean field case, that the error in the energy in the H1 norm is bounded by the error in the square in the wave function, which is interesting to chemists because the wave function is the fundamental property. It's the fundamental thing we want to know, but everybody optimizes their basis sets to the energy. And so that's good news because that means that that's a valid thing to do, and people didn't know it. And then just to finish off, very last thing with the pictures of what actually happens, you can look at the errors in detail, and this is what you get if you look at the L infinity and the L1 errors. You can see the forms there. And then if you look for the H1 as the final result, this is the asymptotic form of what the error looks like. And you will notice that that is that the core of it, this e to the minus square root m, ends up being almost identical. However, the actual numerics of the errors look very different, but fortunately what ends up happening is that you get the same answer. And the reason for this is because the error is dominated at the origin, as you can see on these plots, is dominated at the nuclear cusp. And that means that it is, in broad terms, equivalent to the L infinity error, because that's the error, that's the supremum norm. So it's looking at a single point where there's the largest error. So very fortuitously, they end up being the same answer. I will not say anything about the last slide, just the conclusions. So commonly used basis sets are complete in the correct sense, is the outcome of this for mean field methods of regular potentials. We can actually use the things that I've shown to develop better extrapolation schemes, and that's already being done. Somebody published a paper on that, and that means that we can get better quality results for less time. And then the thing that I didn't have time to talk about, and I'm not surprised, I didn't think I would, is that to go on to the next step where we're not just looking at the mean field result, where we're including the electron correlation fully, my preliminary result is that actually Gaussian type basis sets are not complete unless you have a very strict set of conditions. And that could be quite worrying for application of this film. So thank you very much for listening. I'm sorry for all the faff at the beginning. I just want to thank my supervisor and a couple other people. And if you have any questions, feel free to talk to me at lunch.